Hello everyone! This is our final video in our Special Cases in Linear Programming series. Once again, I highly encourage you, get practice with these linear programs. I really encourage you to pause the video now, attempt to solve this problem on your own, and see at what point an issue arises that you haven't seen before. Remember that as I go through and solve this, I'm not going to be taking time to necessarily explain in great detail every single part of the question. So please, if you have trouble with any part of the question at all, whether it's the creation of the mathematical model, being able to graph the linear program, or find the feasible region or the optimal solution, please consult the previous videos in order to do that. Here we're going to jump in and assume that we already know all of that information. Once we arrive at an issue, then we'll sort of stop it at that point and explain what's going on. Okay, so jumping in here, we have a problem in which we're asked to solve for the maximum sales revenue. So looking at our mathematical model, we want to maximize, always starting with the three little words, either max or min, in this case max, and then the objective function, the mathematical formula that will allow me to solve for what the revenue is. Well, it tells us that both packages that we're trying to sell here, whether it's the Scholar package or the Varsity package, and using those letters for our different variables, so S for the Scholar package, V for the Varsity package, 10S plus 10V will allow me to calculate the revenue of the two packages combined, subject to the constraints that the notebooks constraint. There will be one notebook per Scholar package, two notebooks per Varsity package, and that has to be less than the 400 notebooks available. Similar with the binders, 3 binders in the Scholar, 2 in the Varsity, has to be less than the 600 binders, and pens, 4 in each, have to be less than the 900 pens available to us. Always, 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 the final constraint will be our non-negativity constraint, that we cannot produce negative amounts of either type of package. So S and V must both be greater than or equal to 0. Now creating the graph for that, starting by graphing our constraints, ignoring the inequality at this point. So constraint 1 should be aligned something like this. Again, I haven't pointed this out for a little bit, so please, again, remember that it does not matter how you label your personal axes. You will come up with the exact same answer in the end. It's just your graph will look like a mirror image of the graph I'm creating here. There is no specific way that you have to set your graph up. The only thing that I highly encourage you to pay attention to is if you are doing an assignment or if you are doing a test, in most cases, I will have already labeled the two axes. So make sure you pay attention to the way I've labeled the axes so that when you create your graph, it will look identical to mine, not a mirror image of mine, which will make it much more difficult to try and identify points if you're trying to almost think backwards of what's going on. So here I've decided to put the Varsity package on the y-axis and the Scholar package on the x-axis. So now graphing constraint 2, followed by constraint 3. And once all of our constraints are graphed, we now take into account the inequality. Constraint 1 was a less than constraint, so we will shade towards the origin. Constraint 2 was a less than constraint, so we will shade towards the origin. And also constraint 3 is a less than constraint. So once again, we will shade that towards the origin. So now we look, do we have a feasible region? Well, yes, we do. This region here is shaded by all 3 of those constraints at the same time. So the first special case we looked at was infeasibility, where we didn't have a region that was shaded by all of the constraints. That's not an issue. We do have a feasible region. The second issue we looked at was unboundedness, where our feasible region was infinitely large. Well, that's not the case here. And remember that with that infinitely large feasible region, sometimes it's a problem and sometimes it's not. It really depends on whether we're doing a maximization or a minimization problem. Okay, but we don't have any of that issue here because we do have a fully constrained feasible region bordered on all sides by some constraint. So our one non-negativity constraint, our other non-negativity constraint, constraint 1, constraint 2, and constraint 3 all bind that region. So we do not have an issue with our third special case that we saw either. In our third special case, we saw something called redundancy, where we have a constraint that makes no impact on the feasible region. But that's not the case here either, because we can see that constraint 1 has an impact, constraint 2 has an impact, and constraint 3 has an impact on the feasible region. So redundancy isn't an issue here either. So without any problems so far, well, we're really at the next step of going and now graphing our objective function on here. So our objective function was 10s plus 10v. And again, we haven't done this for a little while in these videos. Remember, the next step we do is we have to just choose some arbitrary number to set that equal to. Well, if I choose a value which is a multiple of both those, and a value that when I do the division will sort of scale nicely onto this scale, I'm going to choose 1,000, as 1,000 is clearly a multiple of both 10 and 10. And if I sub in 0 for s, I will notice it will be v is equal to 1,000 divided by 10, which will give me a nice point on this graph. 100 is a very clear point to put on the graph. And then similarly, I would get also my other point to be now 100, 0. We graph that. Well, remember that objective function, that's not where it's going to stay. That is just our starting point for the objective function. And now, whether this is a maximization or a minimization problem, we want to either slide that objective function to the closest point it can possibly hit in the feasible region, in the shaded green region, the closest point to 0, 0 if this were to be a minimization problem, or the furthest point from 0, 0 if this is a maximization problem, which it is. So now I'm going to slide that line as far as I possibly can away from the origin, and now we come up and we see what our third special case in linear programming is. What we have here is something known as alternative optimal solutions. And the reason why this comes up is because our objective function line has the exact same slope as one of our constraint lines. The slope of this objective function is exactly the same as constraint 3. So this line completely overlaps constraint 3, and really what is happening here is that we have a whole bunch of possible optimal solutions. We have an optimal solution that can be chosen as any single point between this intersection point and this intersection point. Any point I choose along this line, so again, I'm not doing any math to solve for what the actual solution is. It looks like one optimal solution would be choosing to make 150 roughly scholarly packages. Remember, we would have to do math to solve for exactly what that is. And somewhere a little below 100 varsity packages. But just as likely, I may have chosen this point here, in which case I'm making somewhere around 100 and, I don't know, somewhere around 100 of each package. Any point I choose on this line will be an optimal solution, meaning that it will derive the exact same sales revenue, the most sales revenue I can make. At this point, we've seen our 4 special cases in linear programming. The first case we saw, infeasibility. When we have infeasibility, it is impossible to complete the question and to find an optimal solution. The second case we saw was unboundedness, which is an issue when we have a maximization problem. And again, that leads to an unsolvable problem. Infeasibility and unboundedness, when they are an issue, we cannot proceed. We cannot find an optimal solution to the question. The next 2 cases we saw, redundancy and now alternative optimal solutions, we can go and get an optimal solution they just end up either causing a bit of a headache, like redundancy. Redundancy isn't necessarily a complete roadblock in our problem. It just adds extra calculations that we don't really need involved in the model. Here, alternative optimal solutions, this is actually kind of a good thing. This gives us an ability to make a decision based on some other factor. Maybe I want to get rid of more pens than I want to get rid of notebooks. So within all of those possible optimal solutions, I will choose the solution that can get rid of the most pens for me. When we have alternative optimal solutions, we actually have increased flexibility in our problem. Okay, we still have a solvable problem. We can still find the maximum sales revenue. We can still find an optimal solution. There's just more than one optimal solution. But no matter which one I choose, I will still end up with the exact same maximum sales revenue. Thank you very much, everyone. Please, from this video series, know how to identify each of those special cases and know whether that specific special case leads to a problem where I can no longer proceed with the question, where I cannot find a solution, or whether I am actually able to go and solve the problem and come up with a solution. So knowing how to identify the special case and knowing whether that special case leads to a solvable or an insolvable linear program will be the key out of this series of videos. Once again, thank you, and please email me with any questions that you may have.